All right, chapter 13.
Touch the sky. What makes a business a business?
When you touch an object and it feels warm or cold, what is that really telling you about the object? Here I have a metal hard drive and a book, and I'm going to ask people to compare their temperatures. Which one do you think will feel warmer, the book or the hard drive?
The temperatures.
Yeah, tell me if one is hotter or colder, or if they're the same temperature. How do they feel?
This is slightly cooler than this one.
Yeah. Oh, that's warmer. Yeah, way more.
Yeah, agreed.
I'd say the hard drive is a lot colder than the book. I don't know, because the book's got more knowledge.
Why do you think that is?
Metal's normally a little bit chillier if you leave it in a cooler temperature.
Well, what if I said that they're both at the same temperature? What would you say?
So you're lying.
But really?
I think you're lying, yeah.
Oh, jeez. Well, maybe the way I can prove it is I have an infrared thermometer. What do you think we're going to see?
I think science might be able to answer that. And I'm not a scientist.
Make a prediction for me.
I still think that's cool, though.
Would you bet me money?
I do it because I don't have any cash. So, yeah.
Let's measure the temperature of the book.
Okay.
What do you see?
19.0.
Okay. So measure the temperature of that.
19.0. Alright, well now I believe you.
I'm trying to actually figure it out, actually. Trying to figure out why they would be the same temperature. They don't feel the same temperature, though.
So why does that feel colder if they're basically the same temperature?
Good one. Do you have the answer?
Well, I'm coming to you guys for answers.
We're creatives, not intellectuals.
Well, create an answer for me.
I'm not a scientist. Come on, you tell me.
Well, I'll try to answer that question with another little experiment. Here is an aluminium block and
Ooh, nice and cold.
a plastic block. How do their temperatures compare?
Completely different. Completely different.
This is much colder.
Yeah.
Yeah?
Yeah, this actually feels colder.
Let's take this to the next level. I'm going to put an ice cube on both plates. What are we going to see?
Well, I'm guessing it would stay solid on this one and melt on this one.
So it's going to melt on the plastic but stay solid on the aluminium.
Yes, but maybe I'm wrong.
That one will melt more quickly than on the aluminium block.
I think so. I think they're colder.
Yeah, because it's cold.
Let's
I
actually...
think they're going to go the same.
All right, so we put an ice cube on each of those blocks.
Wow.
What are you seeing?
Well, it is melting a lot quicker on the aluminium.
I can't, it's melting.
This is melting quicker than that one, even though this is aluminium, that's plastic.
So which one felt colder?
That
This
one.
How does that make any sense?
I have no idea,
Could aluminium be bad for the environment?
How would aluminium be bad for the environment?
Well, it's thawing out the ice a lot quicker, isn't it?
So you want the answer?
Yes, please.
It's about thermal conductivity, right? The rate at which heat is transferred from one object to another. So when you felt these blocks originally, I know this one felt a lot colder.
Yeah.
But you know from the other example we did that they must both be at the same temperature. True. Because they've both been outside for a while. We see that the aluminium block is melting the ice faster than the plastic block because it's conducting the heat to the ice cube faster.
Okay.
With the plastic block, it's a worse thermal conductor, so heat is being transferred less quickly to this ice block, and so it's staying ice.
Okay. I believe you.
Make sense?
Yes, definitely.
You know, in our first example, the hard drive felt colder even though it was at the same temperature roughly as the book. And that's because the aluminium conducts heat away from your hand faster than the book conducts heat away from your hand.
Sure, that seems logical.
Which makes the hard drive feel colder,
Yeah.
and the book feel warmer.
Yes.
So when you touch something, you don't actually feel temperature. You feel the rate at which heat is conducted either towards or away from you. Think about this next time you hop out of the shower in winter. It's much nicer to stand on the bath mat than on the tile beside it. Not because the bath mat is warmer, but because it conducts heat less quickly away from you.
Okay, that's a great video. I love Vertesium. He's pretty amazing. Anyways, it's interesting. You're at home. If you're sitting down on a chair that has maybe metal legs or metal handles, if you touch the table, touch the metal, they feel total different temperatures. If you have a metal fork or a metal spoon, and then you have a wooden spoon, and you pick them both up in your hands, the metal one feels colder than the wooden one, and that has to deal with, it's like I said, the rate at which heat moves away from or into your body. Okay. And metals that are good conductors, that's exactly what happens. They move quickly. All right. All right. Where am I? There we go. All right. Temperature is the average molecular thermal energy of a substance. Heat is the transfer from hot or high energy to area of low energy. All right. Conversion units are BTUs, calories, foot pounds, joules. Okay. And 4.184 joules of work is equivalent to 1 calorie of heat. Now, there's calories, and there's calories with a capital C. All right. That's a kilocalorie or a kilocalorie. That is what we process in terms of food. When you eat a serving of food and it's 120 calories, it's actually 120 kilocalories you're consuming. And then your body burns that food and makes energy, which then goes through the ATP and all your molecular stuff and your organisms and growth and everything else that goes on in your body. All right. So now BTUs, where have you heard BTUs before? Probably heating and cooling stuff. Okay. If you buy a new furnace, it usually tells you how many BTUs it has. All right. That's a British temperature unit. That's where it comes from. All right. All right. Nutritional value of work. How high must a 70-kilogram man climb to burn off 1 calorie, capital C, of energy? All right. So capital C stands for 1,000 calories. Lowercase c is just a calorie. All right. Now we know that work equals force times distance, and force is mass times gravity. So mgh, that's equivalent to potential energy, right? So the amount of potential energy you have when you go up is how much work it took you to get there. All right. So if we took 1 calorie times 1,000 calories times 4.184 joules equals 70 kilograms times 9.81 meters per second squared times the height. All right. Multiply these two over, divide that over, and the height comes out to be 6.1 meters for 1 calorie, 1 kilocalorie. All right. Now it says a miniature candy bar, what they call fun size. I don't think that's fun at all. It's way too small. I want a regular size one. All right. Is 120 calories. So if you had to climb 6.1 meters to eat one fun size candy bar, you would have to go 732 meters up. Okay. Now a normal flight is approximately 10 meters. So you would have to go up 73 flights of stairs to burn off that one little fun size Milky Way bar. Okay. Does not seem worth it, does it? All right. Let's see here. All right. Specific heat capacity. All right. Delta Q. All right. Is the change in the heat. Okay. Remember what we said heat is. Heat is the transfer from one to another. All right. M, mass. C is specific heat. The specific heat is a number that basically tells you how fast it will transfer. Okay. Water has a very high specific heat. It takes a long time to get water to boil, doesn't it? It also takes a long time for it to cool off. Cup of coffee stays warm 20 minutes. All right, in a cup. It's open. Okay. If you had a piece of metal that you heated up to the same temperature and put it on the countertop next to a cup of coffee, in 5 minutes that would be at room temperature. All right, not like the coffee. All right, because metal has a very low specific heat. All right, which means it's very volatile. It heats up quickly and cools off quickly. All right, a high specific heat like water. Anything that's insulation has a very high specific heat. It takes a long time to heat it up. It takes a long time to cool it down. Okay, the specific heat capacity of a substance is the quantity of heat necessary to raise the temperature of 1 kilogram of a substance 1 degree centigrade. Specific heats are listed on page 248 in your book. Okay. It says how much heat in calories, lowercase c, is needed to change the temperature of 50 grams of copper from 10 to 70 degrees Celsius. So Q equals MC delta T. 50 grams. Now, look at this. This is where everything has to pay attention. Okay, this is where it gets crazy. This is where people make mistakes. So I want you to pay attention to this. On that page in your book, it gives you all the specific heats. It gives you two different types. It gives it to you in calories per gram degree Celsius, or it gives it to you in joules per kilogram degree Celsius. So if you're using this one, you have to be in grams, and the heat given off is going to be in calories, okay? If you're using this one here, you have to be, it will give you your Q in joules, so you have to divide by 4.184. That's why this is here, to put it back into calories, okay? So 50 grams times this times that gives you 276 calories. Now, if you use the other chart right next to it, you'd have 0.05 kilograms. See, we had to convert the grams into kilograms. And then it's 380 joules per kilogram degree Celsius is the number they gave us. Times the 6-degree temperature change, all right? Take that answer and then divide it by 4.184 joules, because that is the, that's what Q is up here. That's all in joules. And this is going to be, this is actually the joules per calorie. So you actually end up getting calories. And it's pretty close due to rounding, because the specific heat is, it says it's 380, but it's actually a little bit, I think it's like 380.2 something or whatever. And when you do it, it actually would come out to 276. All right, heat change. How much water at 20 degrees Celsius is needed to cool 5 kilograms of aluminum from 80 to 30? Okay, now we're in kilograms, right? So what's that going to mean? That means we're going to need to use joules. So when you're in kilograms, you're going to need to use joules. If you're in grams, you can use calories, okay? As long as everything's the same, you're okay. MC delta T loss equals MC delta T gain, all right? So whatever heat was lost by the aluminum, okay, is going to be gained by the water, okay? So you have 5 kilograms of aluminum. Its specific heat is 920. See, very low number compared to this. The temperature change is going from 80 to 30, okay? So you're losing 50 degrees Celsius. Equals the mass of the water times the specific heat of water, and the temperature of the water is going from 20 to 30, so it's going up by 10, okay? So you have 230,000 is equal to M times 41.84, and you end up with 5.5. All right, melting and freezing. The heat of fusion is an amount of heat that's needed to be added or removed to completely melt or freeze 1 kilogram of substance at the freezing or melting point. So Q equals MHF. Now, if you think about this, all right, if you have an ice cube and you throw it in water, all right, it's going to make the water get colder, and the ice cube is going to start melting, all right? If you have a glass filled with ice, okay, and you put some water in it, the temperature of that water will be 32 degrees Fahrenheit or 0 degrees Celsius, all right? Until all of that ice is melted, it will not get any warmer, okay? Once all the ice is melted, then it can start to move up, all right? And that's due to the heat of fusion, all right? So when you're in a solid, you're going to heat it up to a liquid. You will not increase the temperature of that liquid until all that solid's melted, all right? That's what's supposed to happen. Vaporization and condensation, same thing on the other end. You have a liquid. If you want to turn into a gas, you have to vaporize all of that liquid into gas. Once all of it's turned into a gas, then it can heat up past that point. Same thing the other way. If you have a gas and you want to cool it, it will start to condense and it will form a liquid, but that liquid will not get any colder until all that vapor has been taken care of. All right. Sublimation is going straight from a gas to a solid or a solid to a gas. An example is dry ice. All right. You take dry ice, you put it out there, and it turns right into a gas. All right, it's all smoky. They use that for special effects and stuff like that. They also use it in the medical field because dry ice can be so incredibly cold. Okay. In this chapter, you are going to be taking stuff, and you are going to be running through the math portion of taking things from a solid and making it go into a liquid. There's basically, you have to cut everything into little tiny sections. One section being, I am a solid. How much energy do I need to get it to get from whatever temperature it's at to the melting point? That's one section. Q equals mc delta T. If that solid then goes into becoming a liquid, you then have to use the heat of fusion, all right, the QF. Take that number, multiply it by the mass. That amount of energy gets it to the liquid stage. Now you use mc delta T for the liquid. Take it to whatever temperature you need to take it to, okay? If it goes off, if you're going to go to vaporize it, then you take it to the boiling point. Do Q equals mc delta T from the one point to the other point for the temperature-wise. Then you have to do heat of vaporization, all right? MQV. The heat of vaporization is a huge number. It takes a ton of energy to vaporize anything, okay? Very, very hard. Melting is one thing. Vaporizing, ton of energy, okay? So you'll have to go from there. Then you're at the boiling point, okay? Now you want to heat it past the boiling point. Now you have to use mc delta T for the vapor portion of it, all right? So you could go from ice to water to steam. They all have their own C's, okay? And then if I give you a question, it says, hey, let's take a kilogram of ice at minus 40 degrees and bring it to 50 degrees centigrade. That's 3 stages. Heating the solid up to the melting point, heat of fusion, and then from the melting point to 50 is for the liquid. And then you add it all together, okay? Those are the types of questions you're going to see in the test. Those are the types of questions that are going to be on your homework, all right? Pay attention to your units, all right? Make sure you got the right units when you're doing it, okay? Good luck.